Valenti is an associate professor of physics and astronomy at UC Davis. He received his PhD in physics from the University of Ferrara, Italy, in 2008. Before joining UC Davis, he was an assistant project scientist at UC Santa Barbara and the Lick Observatory, as well as a National Institute of Astrophysics fellow. Currently, his work focuses on supernovae, and particularly finding these explosions quickly to understand how they happen, what causes them to explode, and the systems that leads to these explosions to begin with. And I always find these kinds of objects particularly exciting because first they're an explosion, which is already pretty cool, but also because they happen on timescales that are relevant to humans. Like I can watch a supernova happen in my lifetime as opposed to galaxies, which take billions of years to do anything interesting, which is really rather rude. So we're in for a treat tonight as we learn more about these objects, and I hope everyone enjoys the lecture. It's all yours.
Thank you for the introduction. My name is Stefano Valenti, and I will speak about supernovae. So I will actually the outline of my talk is actually two different topics. At the beginning, I will try to tell you what a supernova is and how we observe them, which kind of data we get for them for the supernova, and then I will try to discuss a bit what are the open questions about supernovae. We observe them since 1,000 years, but we still have some open questions that we cannot answer. The first part of the talk, I will finish discussing how we discover them today, and in particular, a project we are doing to discover them very early. It's called the Distance Less Than 40 Megaparsec Supernova Search. And then in the second part of the talk, hopefully in the last 20 minutes, I will speak about a different kind of object, neutron stars. Neutron stars are a really cool object, and they are the remnant of a supernova. But then if they are in binary system, they can actually merge together and produce gravitational waves. And that was a big discovery that was done in 2017, and was the starting of this new astronomy, multi-messenger astronomy, connecting electromagnetic signal, gravitational waves, neutrino. And I will end the talk with the discovery of the first neutron star merging. That was a pretty cool discovery. I was part of it. I'm really proud that I was actually observing it. So let's start then with supernovae. So what is a supernova? Supernova is the last part of the evolution of a star. Stars are formed by they are formed, they evolve, they produce a lot of bunch of elements. Then finally, some of the stars explode as a supernova. When they explode, a lot of material is ejected at high velocity in the universe, and then 1,000 years after the explosion, you can actually see the remnant of the supernova. And here is an example of a video where you see how a supernova explodes, and then we leave the remnant of, this is the Crab Nebula that we can observe today. This was a supernova that was exploding more than 1,000 years ago. And so this video clearly is setting the interest that I have in a supernova. So what I try to do in my research is connecting the evolution of stars, the way how they explode, and the remnant that they leave after the explosion. I mentioned that a supernova gets really bright when they explode. You can see here, these are actually real data. This is a galaxy, and suddenly you see a new spot in this galaxy. This is a supernova is exploding. And when it explodes, it gets really bright for a few weeks, for months, and actually you can observe it. And if it's near enough, you can actually observe for a couple of years. And so some type of data we get is something like this. We measure the brightness of the supernova as a function of time. And depending on the shape of the brightness, we can actually distinguish different kinds of supernovae. For example, just to give some example, here are again real data. Here's the brightness of some supernovae, and they can slowly rise in 100 days. And we know that actually these kind of objects are connected to blue supergiant. We know they explode as a supernova, and they have a brightness changing as a function of time that looks like this. If they get very bright quickly and then they stay constant for some time, we also know which kind of object these are. These are red supergiant. So these are two kinds of stars. So the red supergiant are very large stars that are red because actually, since they're really large, the surface temperature is relatively lower than blue supergiant. Blue supergiant are really hot stars that are more compact, and so they're more hot. Red means cold and blue means hot for stars. There are also other kind of objects. For example, if their brightness changes bell shape, we know that it's more likely these objects are coming from Wolf-Rayet star. Wolf-Rayet star we'll discuss in a bit are all other cool stars that lose this envelope of hydrogen that they have on the surface. Recently, we discovered some really bright objects. We call them superluminous supernovae, and we believe they're coming from very, very massive stars. But this is still an open question that today we don't have an answer. And finally, more recently, we also have observed some objects that evolve very fast. And also for those ones, we actually don't know what is the progenitor. But the brightness as a function of time is not all information you can get from the supernova. You can actually, if you put a prism in front of the light coming from the supernova, you can split the light in colors, okay? And so, in other words, you can get what is called a spectrum. A spectrum is just the photons, the flux that you get from the light that you get from the object as a function of the color. And spectra are super useful. Actually, from spectra, we can get a lot of information about the supernova. We can, depending on which lines we see in the spectra, depending which is the composition of the supernova, we can actually distinguish different kinds of supernova. If we see hydrogen, we see that we know that it's a type 2 supernova. If there is the silicon, we think it's a 1A supernova, and so on. I don't want to bother you too much with all the type of supernova. I just want to give you an idea of how useful the spectra are. And of course, when a new supernova explodes, we are not only getting one spectra, but what we try to do is to get a sequence of spectra. And sequence of spectra are very useful because while you're looking, consider you're looking in some clouds. If the cloud is very dense, you cannot see too far away. But as soon as the clouds will spread out and you start to see became less dense, you actually can see inside the clouds. And this is what we do with supernovae. When they explode, we get information from the surface of the star. As the supernova is exploding, the density is going down, and you can see inside the supernova. And so tracing the spectra as a function of time, you can have information of different layers of the supernova while it's exploding. This is pretty cool, and these are the main two observations that we do to study supernova. We get the brightness as a function of time and the spectra as a function of time. So now that you know which kind of observation we get, what we do, we collect all this brightness, that means light curves, we collect all the spectra, we put this information together with information about the galaxy where the supernova exploded. Is an old galaxy, is a new galaxy, is a crowded region, and putting all this information together, we can then try to understand what is the progenitor that's exploding as that supernova. And so this is pretty cool, and so for a lot of years, people have I have searched supernova-looking galaxy. So here you have a galaxy, you have M82, and here is a galaxy, an image of the galaxy a few years after, and you see a new dot here. This is a supernova exploding in this galaxy. So there have been a lot of people searching for supernova, and actually there is a very important supernova search done here at Lick. Is the Lick Observatory supernova search. It's done with the KITE automatic telescope. Actually, I don't know if you can actually see, walk in there and see what is the telescope. But this search for supernova is active since 1997. I've discovered a lot of supernova. I've done a really good job. However, in the recent year,
Can you maybe go one slide back?
say again?
Can you maybe go one slide back?
Sure.
Appreciate it. So, going to the, like when you keep those two side by side, so the blue circle over there is like where the star exploded?
Correct. So these two pictures are actually different depth, right? So you can see here a bit more clearly all the stars, but actually they're all the same. And you can see that this object is missing here. And the supernova was a star, and when it was just a star, it was not visible because this is not our galaxy. And then as soon as the supernova explodes, it gets so bright as the full galaxy in few hours. And so it's pretty cool. A supernova can reach the brightness of a galaxy, and just to remind you, a galaxy is 100 million of stars. So in few hours, a star can get bright as 100 million stars altogether. So it's pretty cool. Okay, so the Lick supernova search was is a really cool supernova search, but actually in the last few years we are changing a bit the way how we discover supernovae. The technology is improving, we are having an advancing technology, and actually people are starting to use wide field. Instead of point single galaxy, they can use wide field images to actually get a lot of galaxies at the same time. Here is one picture where you can see John Torrey, an astronomer from Hawaii, showing this big CCD. This is mounted to a telescope of 1.8 meters. It's the Panoramic Survey Telescope Rapid Response System, the PanStar search. And just to give you an idea, this camera can observe 7 square degrees in one shot. The CCD is a bit larger than the one that you have in your phone. It's 1.4 billion pixels. So it's pretty amazing. They had first light in 2006, and since then they are discovering a lot of supernovae, even though they are concentrating more now on comets and asteroids. They are discovering, is the major survey that is discovering comets and asteroids. A more recent search for supernova is the Zwicky Transient Facility. This is much more recent. The first light was in 2017. They have a 47 square degree camera that is mounted to a 1.2 meter telescope at Palomar, so nearby here. And the cool thing that not only they're actually discovering supernova, but they set it up also the other telescope to follow up supernova as soon as they explode. So they discover the supernova with the 48 inch, and then they follow up with the 60 inch and the 200 inch. So it's pretty cool. They are also discovering the majority of the supernova we discovered today. Just to give an idea, here are some of the big wide field that have been used to discover supernovae. I mentioned the ZTF1, 47 square degree. I mentioned PanStar, and we are all looking forward to have the LSST coming online. It's not as big as ZTF, but actually is mounted on a very large telescope. Okay, and just to give you another idea how effective these wide field cameras are, here you can see the full sky, and you can see how they can cover the full sky in very short time. They can basically cover the full sky in a few days. Here is a sample of ZTF released in 2022, and here is another of these wide field search, the automatic survey for supernovae, and this is their coverage of the sky, the full sky. You can see here that ZTF only cover part of the sky because it actually is at Palomar, so actually cannot observe down in this part of the sky. It's really a gold era for transient, for supernovae. Here are all the supernovae we discovered so far, and you can see that the majority of the supernovae have been discovered by ZTF and the PanStar, the two surveys that I was mentioning before. However, even though we have a lot of supernovae, the one that we actually managed to follow up, to classify, is actually a small number of them. We are discovering so many supernovae, or transient, let's call it transient, and only few of those we managed to follow up because we don't have the facility, we don't have the telescope time to actually follow all of them. Another way of seeing this is here is the number of supernovae per year. And you can see that with all this new technology, the number of supernovae is just going to 20,000 new transient per year. That means 50 supernova every day. That's amazing. It's really a gold time for supernova discovery. We are all excited. And so, thanks to all the discovery, let's see now where we are with our understanding of this kind of transient. So, if you want, the first takeaway of this talk is that we know that massive stars exploded as supernovae. They evolved, they became red supergiant, they exploded as a supernova, and they live as a remnant, either a neutron star, either a black hole. We know that because we observed them. We have several objects directly. We have seen some red supergiant exploding. we went back to see the HST images. So HST is a really cool satellite that is observing all the nearby galaxy. And so whenever there is a supernova exploding in a nearby galaxy, we can go back, take an old image, historical image from HST, and find the object that exploded. And then we can go back, we can go after the supernova exploding, year after, to take another image to see if that star actually disappeared. And here is a clear case where a red supergiant exploded and then disappeared. So this is one of the best evidence that red supergiants are exploding as a supernova. I also mentioned before that blue supergiant can explode as a supernova. And also for this, we have direct evidence. In 1987, they exploded one of the most famous supernova in the Large Magellanic Clouds. Supernova 1987A was an amazing discovery, amazing event. And also in that case, we had an image before the explosion that was showing a blue supergiant actually exploding a supernova. The funny thing that until 87A, actually theorists were saying that blue supergiant cannot explode as a supernova. But as soon as they actually observe it, they change the theory and they start to say, oh no, actually also blue supergiant can explode as a supernova. Sometimes theory follow observation, sometimes it's the other way around. Wolf-Rayet star. Wolf-Rayet star, I mentioned before. First of all, let me mention what they are. Red supergiant have an envelope of hydrogen and helium, and they explode still with the hydrogen envelope on the top of the star. Wolf-Rayet star actually lose this mass during the evolution. They can lose mass in different way, and when they explode, if they explode, they will not have any more hydrogen helium. There will be a core of carbon oxygen, and maybe have circumstellar material that has been ejected before the explosion, but in the last phase of their evolution, they are basically bare carbon oxygen stars. How Wolf-Rayet stars lose mass? They can lose mass in two ways. They can lose mass through stellar wind, while during the evolution, there is the radiation pressure that can actually push out the external layer that is not bound to the star, or they can lose mass in binary system. If massive stars are in binary system, they can be stripped by the companion and lose a lot of mass. Actually, this is one of the most efficient way to strip mass from a star. And maybe you are asking yourself, well, but how many stars are in binary system? Actually, there is a large number of stars. 80% of the massive stars are in binary system. Or in multiple systems. Okay, so I already mentioned this is basically still the first takeaway, what we know about supernova. We know that red supergiant explodes as a core collapse. We know that blue supergiant explodes as a core collapse supernova. And we know that Wolf-Rayet star most likely explode as a helium and hydrogen poor core collapse supernova.
How big are red, blue, or ultraviolet compared to our sun? Do you know?
Yes, we know. Red supergiant are something like 1,000 times larger than our sun. In order of magnitude, yes. Blue supergiant, maybe red supergiant, I would say 2 orders of magnitude. Blue supergiant, 1 order of magnitude, roughly. Okay, so I've told you what's the status today. We know about red supergiant, blue supergiant, and Wolf-Rayet star. What are the open questions? Actually, there are still a lot of open questions. We don't know what is the role of binarity. I don't know how important is binarity. We know this is important. I don't know what's the level of importance. We don't know what's happening just before the explosion. We see stars evolving and then they explode, but actually it's really hard to observe a star just before explosion because it takes millions of years to evolve and then hours to explode. And so it's like, you want to see a frame of a movie and it's really hard to get to one frame of the full movie. And so we don't know exactly what's happening just before the explosion.
So you mentioned that these supernovas explode and then they disappear. How much time do you have like a certain time limit that you have between the time they explode and the time they disappear? Have you measured that? Or?
Yes, depending on the type of the object. So as I was mentioning before, in theory, if they're really close by, you can observe them for years because they get brighter and then they get fainter with time. Some get fainter very quickly, and some get fainter very slowly. But roughly, if they are, let's say, in the near universe, nearby to us, we can observe them for a couple of years. And if we would have a larger telescope, we can observe them even for longer, just that they became too faint. But the very important point is that stars to evolve take millions of years. Stars to explode takes hours, days, and so the time scale is completely different. And so this is as we were saying before, is really the evolution of a star when it explodes is really a fast evolution comparing to the evolution of star during the evolution. Okay, so these are open questions that we won't try to answer. So how they lose mass before exploding? What happened in the last days, years before the explosion? And understanding this is very hard. Even though we have thousands of supernovae today, it's really hard to observe supernovae hours and minutes after the explosion. And I will tell that in a second. But let me explain a bit better. So here is a star that loses mass before exploding. Here is a layer that was lost months before explosion. Here is a layer that was more lost maybe years before explosion. But then the supernova explodes, and the velocity of the ejecta is 10 to the third kilometer per second, 10 to the fourth. It's really fast. And so in hours after the explosion, the supernova will completely take the CSM around it. And so already a few days after, you lose information. You will never know again what was the CSM, the material that was lost before the explosion. It takes months and years to be ejected because it's ejected at very slow velocity, but then it takes hours of days to just get eaten by the ejecta. So if you really want to know about this material that's been ejected by the star just months before the explosion, you need to observe star in a scale of hours, days before the explosion. So how we do that? How we observe star exploding, supernova exploding minutes of hour after the explosion? Well, we can just sit here and wait that Betelgeuse will explode, right? We roughly explode in 1,000 years, and you want to get the hours after the explosion. So if you want, we can stay here for 1,000 years, but we need to get that frame, exactly 1 hour after the explosion, exactly 1 day after the explosion. It's really hard, right? Star evolving really long time. And also the technology to observe them, there are several steps that we need to do, right? And in particular, what we need to do, as soon as supernova is discovered, by a new transit is discovered, well, you need to check when you have time at the telescope, right? Do I have time today, if a supernova exploded today? And then I need to go to the mountain to observe it, right? And then I need to hope for good weather, of course. And then, of course, I can take a spectra, confirm this is a transient, and then do this multiple times. But the time you do this, you are too late, right? So it's really hard to get minutes hours after the explosion. Unless you change the approach, and instead of using the canonical way of going to the telescope, you can use robotic telescope, right? As soon as the survey will discover a new object, you can trigger your robotic telescope that is available 24/7, get a nova observation, confirm the supernova, and then observe again multiple times within 24 hours. And this is what we try to do. Here is the collaboration I'm part of, the distance less than 40 megaparsec. Here are all the students, postdocs that are working in this collaboration. It's basically a collaboration between UC Davis, Arizona, and the Rutgers University, and other people are also involved. They are doing great science, and I will highlight a couple of results. I don't have time to highlight more, but if you want to ask more questions, I'm happy to answer after the talk. Okay, so what we do, we use 3 robotic telescopes, small telescope, 50 centimeter, one in Canada, one in Chile, one in Australia. We observe nearby galaxy every 24 hours, okay? If they are in the south, we can observe in Chile and Australia every 12 hours. If in the north part of the sky, we can observe every 24 hours. We get an image, we compare with an old image, and we discover a supernova. Can you see the supernova? Anyone? Do you need some help? There it is! Of course, when we get a new image, we don't do this game with eye, because it takes time, right? And so what we do difference imaging. We take the new image, we subtract the old one, and all the sources that are variable will be visible in the difference imaging, and you can clearly see the supernova here. We do this every night. We get candidates hours after, actually 5 minutes after the image is taken. And as soon as we discover a new supernova, we trigger another network telescope. So the network telescope, robotic telescope for the search is the Skynet robotic telescope network. For follow-up, we use the LCO network, where I was as a postdoc, and that also is a robotic telescope around the world. And we observe as much as we can, okay? And we observe, we call classified object, we get the data, we get this sequence of spectra, sequence of photometry to analyze the new supernova. Let me highlight one of the results that we published this year. Jennifer, she's now actually a support astronomer at Gemini. We were observing this supernova, and what happened is that here is the supernova, and here is the CSM that has been ejected just before the explosion. The photon coming from here can ionize the CSM, and if you take a spectra early enough, you can actually see this this feature, very narrow feature, that is our ionization lines, that is just the CSM that is ionized. And so you can see here that you get a spectra 1 day after the explosion, and this feature disappeared already 3-4 days after the explosion. So she was analyzing this beautiful object, and she was confirming that red supergiant lose a lot of mass before exploding, okay? Theory, I can still not understand that. We know how more or less how red supergiant lose mass, but the amount of mass they lose is more steady. The one that you can measure hours after the explosion, we see that is actually much more than is expected by theory, and we still need to understand why. Okay, this was just one highlight. I want to discuss now, mention other kind of star, right? We discussed about massive star exploded supernova. What about small star? Well, first of all, the number of small stars is what happened to small stars. How do they explode as a supernova? Well, first of all, the small stars are actually much more numerous than massive stars. So, a star that explodes as a supernova, core collapse supernova, there is one every 200, 300 small stars. Okay, so the number of actual small stars is much larger. But they do not explode as a supernova. They evolve, they become red supergiant, the red giant, and then they give this beautiful picture that we see with the HST images. They became planetary nebula. So basically, there is a compact object in the center that is ionized material that has been ejected before the explosion, and you see these beautiful planetary nebulae that are visible in the sky. So this object in the center, blue hot object, is a white dwarf. Now, white dwarfs are also a very cool object, and just to give an idea, you can take the sun, and here is the Earth. This is in scale, more or less. Here is the Earth comparing to the sun. You see this dot here? Now take the sun and compress the sun to the size of the Earth, okay? That's a white dwarf. White dwarf has roughly a mass of a sun, roughly, but is the radius of the Earth. So it's really compact object, very dense, very blue. And if you want to observe then, you really need to use HST images. Here you see all these little dot here. These are all white dwarf in a nearby global cluster. And just to mention one of the white dwarf that is most famous, Sirius A and Sirius B. Sirius A is a main sequence star. Sirius B, this dot here, is a white dwarf that is in the binary system with this main sequence star. Just to give an idea. White dwarfs are really cool because actually the radius of the white dwarf change with mass. If you increase the mass of the white dwarf, the radius shrink. That's really strange. You're increasing the mass and the radius is shrinking. And actually this was the calculation that Chandrasekhar did while he was traveling to UK. It was 20 years old. Anyway, he noticed that if a white dwarf is more massive than 1.4, the radius should be 0. So basically, 1.4 solar masses is a limit for a white dwarf. You cannot have a white dwarf more larger than 1.4 solar masses.
What solar mass?
Solar masses. So in astronomy, since the mass are really large, we measure mass in the mass of the sun. Okay. So a white dwarf has a mass of the sun, or the limit for white dwarfs is 1.4 times the mass of the sun. Okay. Sorry, that's a really. I'm sorry, I forgot to mention. Okay, so white dwarfs do not explode unless they are in binary system. If they are in binary system, the white dwarf accrete material from the companion, reach the limit of 1.4, and explode as a thermonuclear supernova. That's pretty cool. And we can see them exploding, but actually we don't know if the companion of a white dwarf is a giant star or another white dwarf. If they are two white dwarfs merging together, or if they are a single star with a companion, large companion. And there are theories that say that if you catch the white dwarf exploding in a binary system hours after the explosion, you can see the white dwarf illuminating the companion, ionize the companion. You can see a bump in the light curve in the brightness at the early time. Let me skip this, and this is another result from the LT40. Griffin Ozenzaiden, that actually just got a faculty position at UC San Diego, was a graduate student at the time. We were observing this supernova, and we see this bump in the UV that was a clear evidence that was a companion star that was not a white dwarf, but was actually a bigger star. This was a pretty cool result. Okay, I don't have time to highlight more results from the LT40, but I want to finish with this story about change a bit topic and discuss about neutron star, about gravitational waves. This is another cool topic that, as I was mentioning, got really important in the last few years. In order to discuss this, I need to introduce another object, neutron stars. Neutron stars have been predicted by Zikiki and Bade in the 30s, and they should have a radius of 10 kilometers and solar masses between 2 and 3 solar masses. So again, take the sun, compress to the size of the Earth, and you get a white dwarf. Compress to the size of Davis, 10 kilometers, and you get a neutron star. Okay, so it's pretty dense. Okay, even more dense than white dwarf. The other thing that I need to mention is gravity. So the Newton definition of gravity is that forces attract each other, but actually, if you want to discuss about gravitational waves, we need to change the way how we consider gravity, and we need to consider the Einstein general relativity theory. And we need to consider that gravity is not anymore an attraction force, but gravity is a curvature of the space-time. The Earth is not rotating around the sun because it's attracted by the sun, but because the space-time is curved, and this is how the Earth go around the sun. If you have orbiting each other, around each other, they will then curve the space-time and make this ripple in the space-time that are called gravitational waves. Okay? And so people have been searching gravitational waves. These are pretty cool. Here is another example. Is a model of two neutron stars merging together, and as soon as they merge, they produce this strong signal of gravitational waves that can be detected far away from the merging. Here you see the wave, gravitational wave that is propagating the space-time, and then will travel in the universe and reach the Earth. And when it reaches the Earth, the gravitational wave will make this ripple in the space-time, and so the Earth will actually wobble a bit, right? This, of course, is exaggerating. It's just a cartoon, but that's the idea. And so, 10 years ago, roughly, there was a new experiment, the LIGO experiment, that wanted to detect gravitational waves. The LIGO experiment is really cool. Unfortunately, I'm not involved because directly, but it's pretty cool. So what they have two mirrors, and they have a laser that is sent between the two mirrors, and then the lasers are in phase, and so when the light is coming back from the mirrors, will actually interfere and basically disappear the light. So you see the light going to the mirror, coming back, have interference, and then basically go back to the detector. And as soon if the two mirrors, the two big masses are moving, stretching because of gravitational waves, you will see a signal in the detector. This is an amazing instrument that is really sensitive. So gravitational waves are really hard to detect. So I wanted to be involved. But the best that I could do was just a LIGO model. So here you can see, and the cool thing that actually, if in order to have the sensitivity of LIGO, if the mirror will move like one step in the LIGO piece, the two arms of the LIGO detector should be actually much further away, roughly basically close to the nearby star. Okay, the cool stuff about gravitational waves that when a gravitational wave is produced during the merge of two neutron stars, they don't only produce gravitational waves, they also produce gamma ray burst, electromagnetic signal, and neutrino, and actually there is a multiple signal that you can detect. LIGO is running several runs, and they did amazing job. In 2017, there was a Nobel Prize for the discovery of two black holes merging together. And so we were really interested, we were really excited, we wanted to work with LIGO. And so what we did, LIGO, whenever they detect a gravitational wave merging, they are telling us which region of the sky is coming these gravitational waves. And so what we did, we decided, okay, let's take our galaxy, and whenever LIGO gives us the region from the gravitational waves coming, we can observe this galaxy and see if we detect the transient, we detect the electromagnetic counterpart. And so LIGO is a big collaboration, and so before starting, they asked us to sign a memorandum of understanding. They asked us to say, they were telling to us, if you discover something, please keep the secret. We want to release the discovery together, okay? Keep in mind. Okay, so August 17, 2017, LIGO detects a gravitational wave. Here is and also there was a gamma ray coincident 2 seconds after the LIGO detection. Here is the LIGO detection, here is the gamma ray. And so what we do, we point the galaxy in the Fermi and LIGO region with the LT40. Here is the Fermi region, here is the integral still, and then the LIGO region in green on the top. It will appear in a second. And then it should appear. Here it is. Okay, here is the LIGO region. And so what you can do, you can go here and search here in the intersection with this region to observe all the galaxy and see if you detect the electromagnetic counterpart. And this is what we did. We went, and here what we got. The LT40 discovery of the electromagnetic counterpart of the first neutron star merging event. We were so excited. I want to show you our Slack channel. So there was a student, Sheng, that was in charge of everything for LIGO, but exactly that day, from Davis, he decided to go shopping with the girlfriend in Berkeley, okay? I don't want to tell you what else happened. That day, we were really upset, but we managed to detect the object, we managed to release our discovery, and it was a big result. So we basically, here is the LIGO detection. This is a movie, and the amazing part is actually that what we observed was exactly what was predicted. People predict the object be very blue at the beginning and red later on, and people predict that actually neutron star merging should produce a lot of gold. Before this discovery, most of the people, there was the idea that the gold is produced in supernovae, but actually with this discovery was a confirmation that most of the gold that we have here on Earth is actually produced during the neutron star merging. Merging of neutron star. It was an amazing discovery. Basically in one day, we were able to prove that neutron star merging produced gamma ray, gravitational waves, and electromagnetic counterpart. We were measured to measure the speed of gravitational waves. We measured to discover that most elements are produced in gold is heavy element. Gold is produced during the neutron star merging. And this is why it was really the beginning of the multi-messenger era that is going on since then. And this is why the second part of the talk is called the gold at the end of the rainbow, because we discovered that the kilonova is producing a rainbow from blue to red, and at the end of the rainbow there is gold. Okay, now the last 3 minutes, I'm in perfect time. I want to go back to what I was mentioning before. We discovered this August 17. And remember, keep the secret. Don't go around telling the secret. And so LIGO informed us that they wanted to release the discovery October 16, okay? So August, September, October, 2 months. What do you think about astronomer? How much an astronomer can keep a secret? Okay, so the discovery was August 17. August 18, one of my colleagues, Craig Wheeler, decided to on Twitter, new LIGO source with optical counterpart blow your socks off. Okay, this is keeping the secret. Okay, and so discovery was again August 17, August 18, one day. Okay, it's not finished. August 22nd. Okay. Another of my colleagues decided to tweet something, but wanted to be a bit vague. And so he was just tweeting, if Light and Virgo really have picked up tonight is one of those nights where watching the astronomical observation roll in is better than any story of a human being, okay? And actually, journalists were actually catching this, and they all were saying this, and they were connecting, and they already connected that there was a discovery. HST, we also trigger HST, not us, but other people. And HST has this nice thing that when you observe something, is tweeting something, okay? And so this colleague of mine, Matt Nicol, was triggering BNS merger. So for BNS merger means binary neutron star merging, okay? So another tweet, this was August 22nd, second leak. Okay, let's go on. Okay, September 27, for some mistake, all the internal communication that we were sending between us and LIGO were suddenly released by mistake by this GCN collaboration. Okay, and then one day before the announcement, I got this email saying a journalist called Jonathan Leak, seriously, was trying to contact people to get the discovery the day before the release. Okay, finally, October 16, NSF do the press release. Here is David Sen, my collaborator, presenting the DLT40 discovery to the rest of the world during the press release. So, and with this, I just want to end the talk showing the element table, where you can see that some elements are produced during the evolution of star, some elements are produced during the explosion of star, and most of the heavy elements are produced during the merging of neutron stars. Thank you. Questions? That's a really good question. There are two mechanisms. So for the core collapse supernovae, the very massive star, what's happening is that during the evolution, there is a balance between pressure, that is trying to compress the star, and so gravity and pressure. The pressure, the star is hot inside, the pressure is keeping equilibrium the star. And the way how it keeps in equilibrium is burning element in the center. They burn hydrogen in helium, helium in carbon, carbon in oxygen, oxygen in silicon. But then they arrive to the iron, and all this burning in the center can produce energy and keep the star in equilibrium. But when you arrive to the iron needs energy to explode, to actually burn. And so you suddenly are left without source in the center that keep the star in equilibrium, and the star collapses. Now, a big star of 1,000 times the mass of the radius of the sun, collapsing and becoming a neutron star that is the size of the Earth, you are transforming all this energy suddenly in gravitational in heat, and that's the reason why it's exploding. In addition, in this process are produced a lot of neutrino and a lot of energy, and some of this energy is basically making the star exploding, or making all the material external material ejected at high velocity. That's the core collapse. For the thermonuclear supernova, it's different. You have 1.4 solar masses of white dwarf that is reaching the limit and is starting the carbon burning in a specific condition. It's called the degenerate condition. And if you start a carbon burning in the degenerate condition, you basically have a runaway. So you start to burn and the temperature increase, you burn more, the temperature increase, you burn more, and you produce a large amount of energy in a very small time. So that's really a thermonuclear explosion. So it's really an explosion. While the core collapse is a collapse and then rebounds on the core and producing this energy in this way. So it's two different ways to exploding. These are the two main ones.
about stars exploding, right? We cannot observe what happens to planets when they die, right?
Well, what do you mean for planets to die?
I know Earth is a planet, right? Like,
And
the sun with other white dwarf or the
so the Earth is not exploding. The Earth, lucky enough, will be eaten by the sun at one point. But the Earth is already, there is no source inside. It's producing energy, and so will get colder and colder with time, right? And so it will be a compact object forever until the sun will actually increase in radius and reach the Earth's radius, basically.
Did you make up the last slide?
Say again?
Did you make that slide?
This one? No, this one is actually I forgot the credit, but I just got it from.
So we could find that online.
Yes, online here you can find it. I forgot to put the credit, but
So if you type in element origins online, you can find that?
yes.
That's very cool.
That one and then, okay. First you and then you. Go ahead.
Yeah, question for the supergiant. How do we know the core is made of helium, hydrogen?
How would you know that there is helium and hydrogen? Well, when the red supergiant explode, we can actually measure see the lines in the. So first of all, you can observe red supergiant. If you can take spectra of red supergiant, you see hydrogen lines that are the external layer of the star, even before exploding. We can see red supergiant in the near universe, in our galaxy, and so you can, or in nearby galaxy, and you can measure in the spectra the hydrogen.
So are elements on Earth actually coming from
Yes.
Earth?
The elements on Earth are coming from. So when the universe was created, it was mainly hydrogen and helium, and just a little of other element, and then most of the elements are produced during the evolution of stars. The stars are taking the hydrogen and producing helium, taking the helium and burning in carbon, carbon in oxygen, oxygen in silicon, and so all these elements here. So carbon, oxygen in blue are produced during the evolution of the star. And then when the supernova explodes, it's producing other element, a bit more massive element. And then when a neutron star is merging, it's producing the more heavy element. So actually you can consider the star as a factory of producing element. So a star is burning element and producing more heavy element during the evolution. And then more elements are produced during the explosion. Yes, when a supernova explodes, all the elements are ejected in the universe, and then they are reused in a new star, to form new star or to form new planets, and all the elements on Earth are coming from a supernova exploding millions of years ago. I'm lost track.
There are two blank elements.
Again?
There are two blank elements. 43 and 61. Why are they blank?
Good question, and I think the answer is that these are not produced during. I don't know exactly the answer. My guess is that these are elements that you need to produce in the lab, and you cannot produce during the explosion of supernova, or I don't know exactly actually the answer.
I guess the transuranium elements are missing because they're produced in the lab. But these two, all right. Anyway, thank you.
Just on Earth?
Well, I assume these are all, their colors are what you have observed during the cosmic background, or these explosions they've observed?
Yes, no, well, not all. I mean, predicted, and some observed and some predicted. Yeah. I will take a look. What are these elements? I don't know. Any other question?
What kind of velocity are you observing of the material being injected? Is it like
The ejecta is going at 10,000 kilometers per second. That is pretty high velocity. Depending on the supernova, some supernovae are 5,000 kilometers per second, other 10,000, other 20,000.
Maybe one more question if we have time, sir? No, so maybe one more question.
When when one star explodes, can it cause another nearby to also explode?
Yes, when a star explodes, can emit new energy in the system and can produce new star exploding or can produce the formation of new star. It's actually a cycle. So the dust clouds can form star and then they evolve, they explode, they emit new element in the galaxy and forming new star and exploding again. And so it's just a cycle that is going on several times.
Okay, if everyone can join me in thanking Dr. Valenti for his talk.